each of these categories. Another thing you can do is make system calls faster. And the best example of all that is copy on the right fork, which you're going to implement in lab 4. Another category is actually just implementing new features, like new types of system calls, so that you can make life for programmers better. So we'll talk a little bit about what cool things you can do, or provide programmers new abstractions that help programmers to get their job done. And there are many examples of that, but one of them is memory map files. So instead of using read, write, and close, you can actually access a file or operate on the file directly with memory addresses. And then finally, since you're going to be doing a lot with virtual memory in this the rest of the semester, I'm going to talk a little bit about JAWS, the JAWS memory layout, the virtual memory layout. Of course, if I also have time today, I'm also going to talk about this one trick that JAWS uses, which is the UVPP. You probably have seen a couple of references in it or in the code. It's a very cool trick, although a little bit of a mind twister. And so you're going to be using that in lab 4, and so to explain how that works. So lab 2, in some sense, what you're doing currently in lab 2, correct, setting up the kernel page tables is just the start of actually playing around with virtual memory. Basically, it will show up in labs 2, 3, 4, and it will show up very hard in lab 4. So remember the prime motivation, right, for doing virtual memory was, and I just want to remind people that so that we don't keep the context in our head, is to actually build address spaces. Right? The main motivation was we want to have multiple applications running on the same processor, and each with its own address space. And the idea is that if an application runs in its own address space, then they can't really interfere with each other because they can't even name even somebody else's physical memory. Right? The only way they could do it if a particular piece of physical memory was actually mapped in both address spaces. So if we set things up in a way that physical memory is only mapped in one address space, then it's for applications impossible to refer to another application's physical memory even. So that gives us this great isolation problem. And there's all kinds of interesting issues about, and we talked about this on Monday, about how to set up the address space. And you'll see in JAWS and x86 it's slightly different, but also a lot of things similar. And we've taken out the easy approach, right? We're putting the kernel at the top and user program at the bottom. So every program, every address space for every application in x86 and in JAWS runs with an address space where the kernel is mapped to the top, and that's convenient because then the kernel can refer to user space or user application data structures and arguments very easily. Now, to say a little bit more, we didn't talk a lot about actually the address space layout for the user part, but the way it's structured in x86, and it's actually a little bit similar on JAWS, is that the text part of the program is at the bottom. So you run the shell, the instructions of the shell are actually at the bottom. Then there's the data set, the data pages, which contain the read and write, data structures, and where it's a list or whatever. Then on x86, there's a stack page, and that's it for. And then there's a whole bunch of memory that is available, which is typically referred to as the heap. This is the memory that's dynamically allocated. Right? And that memory goes up to basically a physical memory. So depending on how much machine memory within the physical machine, the heap is either larger or bigger. And so when we looked at SBreak last Monday, what it did actually allocated new pages out of the heap when you call SBreak. The SBreak enlarges the address space with new pages from the heap. Right? And so the homework assignment was to do that same increasing of the address space in a different way. Right? And the reason you might wonder why you want to do it in a different way, right? I mean, like SBreak works, why do it in another way? And the main reason for doing this is that you remember if you call SBreak, you have to supply how much physical memory you want. Right? So they, like, and we saw in the call, for example, S-break it asked for 32 kilobytes of memory. And that's in some ways it's an inconvenience thing, right? Because the programmer has to predict how much memory the program needs and ask for it. But if you ask for a lot and you don't use it, right, you allocate a lot of physical memory for no particular reason. And if you ask for too little, then you have to call S-break a lot. And so current operating systems hardly use S-break anymore, but they all use the same technique that actually you did in the homework. Right? So the idea being you promise the application, oh, you want 32 kilobyte of memory? Here's 32 kilobyte of memory. But you don't do anything as the operating system. Right? You just actually don't allocate any physical memory out of the heap at all. Only at the point when you actually need that physical memory, right, then you actually allocate the pages that actually is necessary. And so, for example, if the shell only needed 4 kilobyte of physical memory, which is actually the case in our example, then the other, the rest of the 32 is actually is not going to be allocated in the homework scheme. Does that make sense? Yeah.
Is this even true for Kala? Clear.
Yeah, that's even true. So, okay, so two things, right? So there's two interfaces to memory allocation. There's the C-level interface, which consists of malloc, calloc, whatever, all those guys, correct? And then those guys internally keep a pool of free memory to actually return things or free pages. And so, but if they need more memory, if malloc, for example, runs out of its own free list, it will ask the operating system for more memory. And in XP6, that was done using S-break. And you're basically doing the same thing, except you don't really allocate physical memory at all. You just say like, I'm interested in having it. Yeah.
So when you return to a program and you say like, okay, you have this memory, but then later you try to allocate it and it doesn't work out,
yeah.
doesn't that create kind of like a weird situation where you told them it was okay, but then it's not later?
Well, there's no work that actually there's not giving them anything in the first place, correct? So either way, like if you run out of physical memory, you run out of physical memory, and whether you know immediately or you want to know a little bit later, both cases are bad. Right? And so there's not a really.
In fact, isn't a little bit later preferable because your program may or may not crash, as opposed to if you try to allocate it instantaneously, it definitely crashes.
Yeah, well, we can debate either side of that. I mean, the whole point of doing it lazily is that you just allocate what is needed at that particular point in time. Right? That's really what I really got. So the programmer doesn't have to think whether I should ask for 64 kilobyte or 32 kilobyte. It doesn't matter. You can ask for a lot and then later use it later.
So S-break you can use less than page granularity, but
not really, correct? Because S-break always allocates by physical pages, by virtual pages. It always rounds it up to it. So you can do S-break of 1, but then the 1 will be rounded to 496.
and you still access like 2.
So yeah. There you go. All right, so let's look at I'll show you my solution for the homework, just to get a little bit of sense how you do it. So the first thing, right, okay, so let me, so the first thing for the S-break, if you're on the part 1 of your homework assignment, you just basically do nothing, right? The only thing we do is increase, whatever proc size to something bigger. And even that you don't really have to do, right? I mean, the only reason we're doing it is just convenient so that like we don't have to modify a lot of checks that are all over the XP6 code that check whether an address is below P size, right? But in principle, you should have to do nothing at all, right? You can just ask, in principle, an application one that needs more memory, you can just ask the reference an address in the heap, right? And then, it's up to the operating system to, if there's space, to actually give it, to the application. And so the mechanism being used, right, just to make sure that we understand what's going on, is that when the processor asks, references some memory address, right, for which there's no page map, which is in the case when we're doing your lazy application scheme, then basically MMU, correct, has no translation from that virtual address to a physical address. And so then the MMU does something special. It can't translate, and so it has to do something special. And the thing that it does special is basically there's a wire running back from the MMU to the processor, which basically generates an interrupt. You can think about it, it raises a 1 on the interrupt line, and so the processor gets an interrupt. In fact, it will also say what kind of interrupt it is, and in this case, we typically is referred to as a page fault. Right? So MMU generates a fault for that address, typically a page fault, and then the operating system gets in charge again of actually resolving that page fault. And of course, the operating system now runs, runs with some set of addresses that were not the ones that it's faulting on, right? So it's going to run into somewhere in the kernel. Yeah. Okay, so let's we can actually look at this, right? And we can run it. So let me. Oops, I want to do this. I want to one. It's handy for when you're doing x86 development to set the number of CPUs to 1. Right? Remember, x86 runs on multiple processors, but you don't really want to deal with all the concurrency crap, at least not now. And so generally what I do when I do this kind of stuff, I actually set the number of CPUs to 1, so I don't have to worry about it. Breakpoint track.cu10 page, so I'm going to set a breakpoint. Continue. So that goes to start the shell. Right now, nothing has happened yet. So I'm going to start the shell. Presumably, the shell will remember the shell does some memory allocation using malloc. But malloc actually hasn't allocated any physical memory yet. So the first thing it does, it does this sbreak. Sbreak won't do anything with the homework solutions, and so at some point, it will actually use that memory that is allocated, and at that point, presumably, we're going to get a trap. So it could be the case that we never get a trap, right? If like shell didn't ask for any additional physical memory, then nothing would have happened. Things would just work. But let's say I think the shell will ask for additional memory, and it did, and so it trapped, right? And it trapped into some address was referenced by the shell. There was no mapping for that address, so there's an interrupt going from the MMU to the processor saying like, hey, there's a page fault for some address, do something about it. Please repair what the damage is. And so, and then we're in the code where the trap is the place where all the interrupts, including page faults, actually, and system calls all arrive. Right? And that's going to be very similar for jobs too. And so now we can walk through and sort of see what actually happened. And so in RC, whatever, the control register number 2, as you figured out, presumably has the faulting address. So the address that the shell was referencing that for there is no mapping. Right? And so let's do one more, and then we can print out A, and the 6030 6348, which makes a lot of sense, correct? Where it turns out, like the shell when it started had 4 kilobytes, 4 pages, one each of 4 kilobytes, so that's 16K. So this area was, the parts of the address space from here to here. That's 4 pages, and so it's referencing exactly the first address of the heap. Right? And since we haven't mapped anything there, we're getting a page fault. Make sense? And then actually the solution is almost trivial, correct? We actually allocate the page from the kernel, from the free list, in the same way that you have implemented, your free memory in free physical memory in lab 2, in the first part of lab 2. And so we zero it out just for good convenience. Let me talk about a little bit later. I'll show you a cool trick with zero field pages. With you will see that an operating system zeros pages all over the place, and you can use VM, the virtual memory system, to do those cool little trick. And then basically we call map pages, right? And so let's look at the before we do that. Before map pages, like the page data hasn't been updated, but we have the physical address in our hand because of the page that we allocated, and we can look at the info structure, and we only care about the user's part, right? And we see indeed there are 4 pages being allocated, half already been allocated, right? So 0, 1, 2, 3, 0, 1, 2, 3, right? And so we are expecting that after map pages and after loading CR3, the more pages will show up. And so the call here is pretty reasonable, correct? A was the address that we're going to map that page. So we're going to map some page, right across the stack. We're going to give that to user space, and we're going to, it's a page size, so one page. We have to translate, of course, the page that we allocated, correct? We have some virtual address, for some, page of physical memory. We need to stick into the page table hardware the physical page number for that address, right? Because the page table hardware can't work with virtual hard addresses. And so there's a call to the v2p, which basically does nothing else than subtracting current base, correct? The way to translate virtual to physical addresses is very simple because we map all the memory, all the physical memories map back into kernel part of the address space. Yeah. So these arguments make sense, presumably. And hopefully something similar like this. And then I'm going to do next, and then we can look back at the page tables. And let's page, we'll see what the scoop is. And voila, we got one more page. Right? And that's that one page we allocated. And in fact, the physical page number for that page is 0D F2B. All right? Make all sense? Everybody got that to work? Okay, and now, the cool part, so we can keep on going. So now we're going to return from the trap. The trap, we'll talk about this next week, the trap will restore all the state of the application. Like the shell, remember, got an interrupt because of the page fault. We sort of repaired the page tables in the background, like the kernel, correct? And now it's just like, oh, shell, keep going running again. And it's going to now dereference that same address again that it faulted on. But this time around, correct, when it won't fault on that address, but it actually is now an entry in the page table. And so it will actually succeed. Right? And so if we continue, we'll see that actually the shell runs, it will at some point ask for more memory, right? And so it keeps on going. Does that make sense? Everybody have that? Yeah.
So when the interrupt is fired, the interrupt is caused by a specific instruction, right?
Yeah.
That instruction always gets re-executed when returning from the interrupt?
In this case, the instruction was not executed, so the EIP, the saved EIP, will be set at the beginning of that instruction.
Okay.
And so then when you return, that EIP that was saved will be popped into the real EIP register, right? In the same way we saw the return of system calls. And again, I will talk about this in more detail next week, and things will work out.
So basically, the permission check happens before the memory stage of the pipeline, right?
Whatever is pushed on the stack, is whatever the state was at the beginning of the instruction, not anything in the middle of the instruction. Yeah, this is called precise interrupts. There's a whole technical term for this, but yeah.
So the OS doesn't keep track of which instruction would have incremented.
No, exactly. This is very nice of the x86. This is one of the features that's nice about the x86. You don't have to think about that stuff. There were processes in the past where interrupts were, as they were called, not precise, and the OS has to go figure out like which instruction actually followed, put the right stuff back in the stack, and all that stuff. In this case, it's trivial. You don't have to worry about it. Yeah.
So the case of syscall is different, right? In the case of syscall, the int instruction actually executes.
Yeah, so the int instruction executed,
right?
Correct? And therefore you enter the kernel, and therefore the EIP points to the next instruction after it.
Right.
It's very nice of the x86 hardware, right? Like you don't have to think about this, just, yeah.
So if you go back to the code, you check if CR2 is less than project size.
Yeah.
Is that similar to saying checking if it had what a breach fault track?
No. Remember that in SBreak we just allocated 32 kilobyte of memory, correct? Well, we didn't allocate it, but we increased the P size to 32 kilobyte of memory. And so we actually, P size is already pointing here, except we haven't allocated this physical memory. And this check, like in a real operating system, you would not call SBreak in advance at all. You would just plainly use the heap. And if there was no page in that address in the heap, the operating system would allocate it for you. So, and the only reason we have it there is that I didn't want to make you forced to do more work and go strip out P size everywhere where it's not necessary. All right? Does that make sense? Any questions about this part of the homework? Yeah.
Okay, so this will, if I allocate like 16 bytes, or do SBreak on 16, and then I try to access the first byte of that page, this will work. But then if my first access was more than 16?
Yeah, there's all kinds of little things that are wrong with this solution, in the sense that like the interaction between SBreak and this pageful handler are a little bit weird. The real right solution is strip out SBreak out of x86 and just use a page fault handler to actually increase the address space. All right? So if you're excited about that, you should go ahead and actually remove SBreak from x86. Make sense? All right, so this is one of the many cool tricks that you can do with virtual memory system. And so we're going to do a whole bunch of more tricks like this, and hopefully to give you a better understanding about like what you can all do with VM or virtual machines, not virtual machines, virtual memory. So just to remind you quickly, right, just to see what happened here. Here's the sketch again, or what the x86 virtual hardware, the MMU. So basically, we have the processor, we have the virtual address, versus the MMU. Correct? The MMU has as input, the physical address of the page directory. So let's say in this case that the physical page number is number 3. Then in memory, in third page in memory, physical memory, there's where the page directory is. And in some sense, with the hardware, it doesn't really matter like what's in it, right, in these set of bits. The hardware is just going to interpret this as 1024 entries. And so, for example, if we would reference virtual address 0, correct, with this scheme, the MMU will say, we're going to use physical page 3, we're going to use as the page directory. I'm going to look in physical page 3. I'm going to look at in the top 10 bits from address 0 to use that as an index into this page directory, in this page. Well, the top 10 bits are 0, so it's going to be the first entry. And it's going to look for a physical page number that corresponds to the page table page. Right? So say it's 5, or someone enter, yeah, 5. And so what then it does, okay, good. Let me take the next 10 bits. I'm going to use that as an index in the page table directory. So the page table directory for this address is 5. So it takes the next 10 bits, which is also 0. And so it takes the next entry. It takes a 0th entry. And in this case, it has physical page number 8 there. And so physical page number 8 actually has the virtual address 0 in it. Make sense? It's just and so that's how the scheme works. Okay, and so what happened, correct, before when we called map pages actually went in and actually filled in the right page table, the right physical number in the page table entry, right? And that was that entry 4. Okay, good. Now the reason I wanted to draw this out is because it actually sets me up to talk about a couple other cool tricks. And one thing to note, correct, is that there is overhead to actually maintaining these page table structures. Right? Because we have a page directory per application, we have one page directory. There's not much, there's like one page, but we might have many, many page table pages, right? Mainly one for every 4 megabytes or something. So it's 524 stands for 4 megabytes. Right? One for every 4 megabytes, we're going to have one page table page. And so there could be many. And so if you think about it, like that may be not actually the best way to arrange things. So for example, let's think about what actually happened when let's think a little bit about what actually is going on with the kernel page tables. Right? Remember, we looked at this code at KVM alloc, and one of the things it did, right, every application has a page directory. 2 applications both have a page directory. And remember, from entry 5 and 12 onwards, it's all kernel, right? Where's the kernel address space? So let's think about this, right? So here's entry 5 and 12. Here's entry 5 and 12. And in fact, this 5 and 12 entry is for application 1. It's going to point to some page table structure, correct? To the start of a page table structure. And that is going to point to the actually first virtual page of actually the kernel part of the address space. Right? So this is going to point to some other physical page. It actually contains the bottom the bottom end of the kernel. Right? The first virtual page of the kernel. So let's think about this guy, right? So let me actually make one more point. When we actually allocated those pages, we actually asked for new physical memory. Right? Every time we allocate a page, and for example, we set up this kernel virtual address space, we ask for new memory. And let me, to make sure that we agree on that, let's just pop up the m.c. So like in KVM, correct? So here we go through, correct, and actually when we allocate, we go through the whole 5 and 12 entries of this page table directly to map that memory. we call map pages, and map pages internally allocates a page table directory, page table pages on the fly. Right? So if you think about this, what's happening with this guy, let's say application 2 is running, well, it's going to have a pointer, or going to have a page directory allocated, that's this guy. It's going to have an entry 5 and 12, a physical page number for a different page, right, that corresponds to its entry of the virtual to the page table, which is going to point to some physical page that contains the first part of the address space of the kernel. Now, these two pages, are they the same?
Yes.
Yes.
Yeah, they're identical, right? Because this is actually, contains the bits of the kernel, and those are the same ones. So this physical page number, let's say whatever, it's 34DB or something like that, that must be the same physical page number that's in this guy, correct? Make sense? So, there seems an opportunity here, correct? What is the opportunity? Yeah, memory sharing, right? There's no reason, there's these. In fact, the entries from up here are identical. They're all going to page to the same, whatever physical page number. And so there's no reason for us to allocate all these additional page table pages, correct? Does that make sense? So you just for fun of it, I did implement it. I didn't see if that actually. So this is the modified setup KVM. It allocates the page table directory because every application has to have its own page table or page directory. It zeroes it out, and then if there is already somebody else allocated earlier a kernel page directory, then we're going to copy that page directory. So instead of but not a shallow copy. We're not going to copy all the pages, all the page table pages, but just a shallow copy. So how does the shallow copy look like? Well, that's all it is. Right? It's a loop going from up here to the top and just literally copying those entries from here to there. Right? And now this guy is going to share again the same page tables as the other guy. Does that make sense? And so I saved memory. Right? And of course, if I want a lot of processes running, this is going to start up. This is going to start adding up, right? Because I'm going to have one basically physical page, one page table for the whole kernel, as opposed to one per process. That make sense? And so this is actually a good change, right? I mean, this is basically for very few lines of code, we actually get a lot of benefit. Of course, a little bit more trickiness. And as always, this code, you've probably seen this in homework too. In the homework too, this code is tricky, right? Even though it's very few lines of code and it's easy, if you make one little mistake, you get strange behavior. I don't know if anybody seen this or you see somebody shaking yes, yes, yes. And then are there people that did anybody get this like perfectly right the first time? So like here's one mistake that I made, which threw me off for a second. I forgot to put I actually had the Mensa here because I was in a hurry, prepared to lecture and thinking hard. And so I ran that. And I was all excited, correct, because I did this. That's only the camera. This. It's like, it works. LS came up. I'm all set. Bingo. Nothing, no problem at all. Actually, keep working. Actually, I'm unlucky this time. When I was at home, I did this. The first thing, of course, that happened was that everything worked perfectly except in the case where we were free. When the virtual memory address space is actually being freed, because the page directory didn't contain zeros everywhere anymore, but could contain some random information because I didn't set it to zero, it actually started to free pages left and right that I never had allocated, right? And the way it showed up is like some applications, 10 applications later actually crashed, and not like the initial application. And this is, I think, one of the things that makes things very confusing because you think like, okay, well, I made a mistake here, or this code has executed once, so it must be perfect, right? It just tends not to be true. So this is something to keep in mind, and it happens to, I guess, the best of us. You make a little mistake, and you get strange behavior, and it's a little bit hard to figure out where actually the error was, right? Because it showed up in the free memory part, and didn't show up. It didn't print out a message saying that free memory. Franz, stupid idiot, you should have mem set that page directory in KVML as opposed to, right? All right, good. With that, since you're setting manipulating a lot of page tables, that puts you on a warning, I guess. Okay, so that was trick 2, I guess. We did lazy allocation. We did sharing page table directories or page table entries. Another cool thing to do, which you'll see a lot, in fact, we will use it in JOS quite a bit, is to actually what something is called guard pages. So the problem is as follows, or at least the things that we want to fix is as follows. The problem that we want to protect against is stack overflow. Right, so the stack is going down, so this way, right? And so when we do procedure calls, right, they push your stack frame on the stack. You've seen in lab 1, and you've looked at it quite a bit. So every time they're going to allocate, another procedure call is going to allocate a stack frame and move the stack pointer down. Right? So what happens? So in the case of x36, and then you'll see this in JOS 2, we have allocated 1 page per stack in total, like 496 bytes, right? And that sits at the below the heap. And so what happens actually is, we keep on going, and we run off the stack. And the stack pointer keeps decreasing. We call it a procedure call that will decrease the stack pointer. What will happen? Well, we'll start writing to memory here, right? And so if the data is right below our stack, what will happen? The recursive call will start overwriting, our data structures in the kernel or in user space or application. Make sense? Does everybody see what the risk is? This is bad, right? Because suddenly you find your program is working. In fact, your data structures are looking perfectly fine, except that some of the first procedure call is basically manually over your data structures. So the standard trick to this is to actually put a page between the stack and your data. And what do you do with that page? Yeah, don't allocate it. Basically, make it not writable, not readable. Just you can't use it. Right? And so the goal is to actually, if you do this, to actually get a page fault. Okay, so you typically put in what's called a guard page here, and that guard page, make sure that actually, if you run up the stack, the page fault will happen. And then, of course, the OS can do different things. So what are the things it could do? Well, one of the things it do is say, like, you run over your stack, stupid idiot, like, end application, correct? And that is what x36 does. But like, what would a real operating system do? Yeah, give you more stack. Exactly like what you did in the homework, right? You can do exactly the same trick. You can actually, allocate, more physical pages, and put the guard page, one lower, right? Of course, that means that somewhere in the address space, you have to have reserved space, virtual space for the stack. But you can allocate it then dynamically on the fly or lazily, right? And so you will use as much physical space actually as you need for the stack and no more. Does that make sense? So this is actually a very, very cool trick. And turns out it's pretty easy to implement, right? So if you look at x36, and you look at fork, actually it's an exit, sorry. So an exit sets up the address space for a user program, and somewhere right here, we actually allocate 2 pages for the stack. Right? So allocating them as 2 times the page size instead of once the page size, and we're going to use that page for the stack. And the reason, and the second page, we're actually just cleaning out. So x36 always is run with this guard page. So we can actually look, we should be able to look back, hopefully, at our page table, and note that, here is our page table, let's see if that's true. And notice here, this entry number, the number 2, or the physical page number 2, notice that it actually has no U bit set. So what does that mean? That means if a user instruction tries to push down the stack or write in that particular area of memory, you're going to get a page fault, right? And so then the operating system gets in charge and you can do something. Yeah.
It's also not this present though. Doesn't that mean it's back to physical memory and we don't want that?
No, well, it depends how you use present. Present means there is a translation, an entry. There's a valid entry, PTE entry. The entry is valid because it actually is filled in, except it's filled in without the U bit, correct? And so this allows you to figure out different things. It just allows you to say, detect that this valid, this entry was set up in this specific way. And, yeah.
Does that entry actually punch through pages physical entry?
No, it doesn't. Well, you can put a physical page number in there, but it won't translate. It will translate if the kernel was referencing to that particular address, correct? Yeah.
So like right now, it would have like physical page number 0 and then the present bit set. Is that what was it?
Actually, it looks like it actually has the this physical page number set. Right? We didn't clear presumably the physical page number. We just cleared the bits. We were lazy. But won't use that. At least a user instruction cannot refer to that physical page using virtual addresses between whatever 8K and higher. Right? So just to we can actually just if you guys will like it. Here's our Stack Overflow program, correct? And you'll see. Okay, let me first show this. Just a little demo that we actually. It's always good to write little programs to detect whether actually your stuff is working, right? Because these are the exceptional cases. So here's my brilliant recursive function. It just calls itself continuously, right? And so at some point it should run up that page, up the stack, right? And so let's see if it actually works. So here's Stack Overflow. I'm going to run it. And it's going to be very exciting. Oh, wow. Oops. That's not what I expected.
You have to recompile.
Maybe okay. What I wanted to see was there's a page. Okay, so shoot. Give me a second.
Because you put the map set in the wrong spot.
Yeah.
Oh yeah. Oh, thank you. We'll see if that actually is the problem. I put it back, right? So, well, it's still a problem. Okay, I don't know what I did. I did something wrong. I should have said trap page fault, correct? And do something. It says panic remap, maybe because actually that thing is not set to 0. But I got to believe something bad happens, which is good. Okay. Well, don't worry. I think it is because my solutions from the homework solution for 2 are interacting badly with this particular piece because of some changes I made. Which I won't debug in front of you because it's not very profitable of your time. Although maybe interesting to see how I suffer. Okay, so this is another. In this garbage trick, you'll do it in a bunch of different places in JAWS, and it's a very, very standard, good trick to use. Okay. All right, so let's keep on going. So another trick, and I know you're sort of starting to get good at this. I can sort of sketch them out instead of completely implementing them, and implementing them incorrectly apparently. So another trick. You can think about it we saw this one memset call, right, where we're clearing out a page. And it turns out the operating system has to clear pages all the time. Right? You set up a new address space, you need to clear out the data part, like C semantics requires the data structure to initialize to 0, correct? And so basically you have to clear out all the data pages. And so that can get expensive, right? With memsets, this is 496 bytes, and so every page, it's 4K of instructions to actually clear out a page. So how could you solve that problem? What trick could you apply to actually avoid having to clear out many, many pages? Or at least do it on demand? Because maybe the page will stay 0 forever and doesn't need to contain anything.
Yeah, you just have one designated physical 0 page and map any.
Yeah. Yeah, so the idea is very simple, right? Now you're experts in page tables. You can have, this is a page table entry. Here's a page table from another. This is the second level entry, correct? And we have some bits here, and we have some bits here. And what we can do first is the operating system, we can allocate one physical page, right? So we allocate, say, physical page, 511. We put a lot of zeros in it, 0 completely out. And whenever an operating system or an application needs a 0 page, good. We can do that trivially, correct? We allocate, we put the physical page number in here, and we're done. 511, both of these guys have a page with zeros in it, correct? Now we have to be a little bit careful, correct? Because one of these applications might start writing to that memory, and we need to detect that. So how do we set the permission bits? Not writable, correct? We should just read, then we're in good shape. And then the next step, correct, is pretty trivial. It's the same as homework. The homework solution, okay. And when one of these guys actually writes, to its page, because it actually wants to write, do something with the page, what will happen? We're going to get a page fault. And what can we do at that point? Well, at that point, we can say, oh, good. Well, we actually allocate the page. Correct? Let's say this is 512. We update this to 512. Make this read write, and we're off the ground. Right? We may still have to put all zeros in it, but we at least don't have to zero out all the other pages that never got written. Because this is another form of lazily zeroing pages in memory. That make sense? This trick of actually putting a read on, setting the read bit, and then later on, making a copy to the point you're going to write is called copy and write. It's a term you will see a lot. And often the acronym is CAP. Okay. To make that, everybody got that? Any questions about this? So that's it, yeah.
If you do a mem set 0 in the application, that would still cost the making a new page?
Yeah, this does only work, right? I mean, the application actually zeroes out a page. The operating system doesn't know about that, right? So that page will be, that's the application. So this is a trick that works inside the kernel, but does not solve any zeroing of pages that the user might do. Okay.
Isn't S-break guaranteed to return pages that are all 0 if it allocates a new page to you?
Oh, yes. I believe that's right.
Okay, so then there's no need to set if you knew you got the page from S-break.
Yes, if you knew the page got from S-break, which the only operating system that does that these days is SV6 or x86, right? Like no other operating system does it that way anymore. No operating system, every operating system supports S-break, but nobody uses it. Any more questions about this?
What do people use if they don't use S-break?
Well, they do what you do in homework too. Lazy allocation. They just reference the page in the heap, and boom, the operating system allocates it for you.
But even then, it's supposed to be 0 out now.
Yeah, that's 0 out. Yeah, it doesn't help with that. It helps if things were like an application has a big data segment, and all those pages of the data segment have to be zeroed out. That's where it happens.
To implement some of these things, people use the available bits in the page table entries?
Yeah. Yeah, so there's a couple bits I think you're referring to, which are called the system-defined bits, which you can use. In fact, you will use them in Lab 4. In fact, one of the things you will do is actually you are going to mark certain pages as copy and write. You will use those bits. You will put the copy and write in those bits. All right? Good questions. All right, so a couple more tricks. We do one of them that's just cool. Actually, they're all cool. We do one that's extra cool because we're going to implement it. So let's take a quick look again at fork. So one thing you see when the shell forks itself, correct? It makes a duplicate of itself. Right? Fork makes a duplicate of the parent address space. So the child and the parent exactly have the same address space. In fact, the child has a copy of the parent's address space. Right? In fact, the first thing you can see here is this copy to VM that actually copies the parent address space, correct? And part of that copying, correct, must happen that page table directories, the PT pages are actually allocated, correct? So all the additional pages that are necessary to translate virtual addresses are copied. Right? And like in the kernel, correct? We did this trick of actually sharing the page table for kernel addresses. The addresses for the physical memory, the addresses that are going to be in the child and the parent are identical. Right? In fact, and so this is, in some sense, it's an expensive way of copying, correct? Because it basically copies a lot of stuff. And is it really necessary that it needs to be copied? If you think about our programs over in the shell, what happens typically after a fork? Exec. What does exec do? Yeah, wipes everything again, correct? So fork first, it's a complete new copy of the parent's address space, correct? And then the next thing it does is exec and then wipes out that address space again. But we just went through, correct, and in fork, and did all that copying. Well, it's presumably not that bad, but make it a little bit more dramatic. And we did all that copying, correct? So how could we solve this problem? Yeah, correct.
Well, we can just make the new the mappings for the new process map to all the same physical pages, but map them read only and then copy on the right order too.
Yeah, so we can just use the same copy and write trick, right? So let's say we have, here's the parent, right? Here's the child, address space. The parent, has some page directory that corresponds, to that. Some page directory that corresponds to this address space, right? That's filled in. That has maybe pointers to, page table directories, right? All that stuff. And so instead of maybe doing this deep copy that actually we're doing here, what we could do is we could do for the child the same thing. We do allocate the one page table directory, correct? But instead of making all these new additional pages, these kind of guys, we just copy the entries in. So in fact, we copy not only the kernel part, we copy the user part too. Right? So we just literally, run through the 5 and the 12 and basically set them all to the same entries as in the parent. And so in a single, one loop, over those 1,000 entries, and boom, we have a copy of the process. Now again, we have to be careful because if the child might actually want to write to some parts of its address space, we don't want it to actually write to the parent's address space too, right? And the whole point of isolation, right? The whole point of isolation was when one process writes, the other process is not affected. So we're going to arrange that this not happen. Well, we could use the same trick again. We mark them all read, and then we do copy and write, right? Because if the child actually references or writes to one of these pages, and we'll get a page fault. In fact, we're going to set the COW bit here, and we're going to see, this is a copy and write page. So when we see a read and we see a write to a page for which only the copy and write bit is set, we know, we should make a copy of that page and then restart the write. Yeah.
We also have to mark all the entries in the parent to read only as well.
Yeah. So yeah, good. So very good. Remember this for lab 4. Yeah, when you do this, good. Better also mark these all. Because if you didn't, what would happen?
Right from the parent.
Yeah, right from the parent, go through the child, correct? And would that be an immediate bug? Would the program immediately stop saying, hey, you guys made a programming error? No, not at all. Correct? It will show up in the 6th exec, something weird happens, and you're like, what happens now? In the same way that I've got this mem set that has all kinds of bizarre effects.
So we still have to do 2 copies of both the parent and the child, right?
Well, what happens at the exec, right? We just wipe this whole directory and it's gone again. And then, if the page is not being shared, then we can just send it to write on the page fault. We don't have to do anything. It's the typical thing that will happen. Does that make sense? It's a good question. So we're really saving literally those copies. You don't have to do it. Yeah.
Well, we need to still do ref counting because if the child forks again, then you can have.
Yeah. So getting your ref counting code, what you're currently doing in lab 2 right is pretty important. It will be more important in lab 4. Make sense? Everybody, yeah, go ahead.
Could you just go over again what happens when the parent wants to write one of the?
Okay, so we're going to, just to make double check, we're going to map all pages, both in the parent and in the child, read only. And now when the parent is going to run again, it probably is likely going to update one of its variables in the data set. So that will cause page fault because it's mapped read only. You cannot write to a page in order to address it to map read only. So that will get a page fault. At the point of the page fault, you can say, and we're going to also set the copy and write data. You can say, this is a page that actually is mapped copy and write. So what I need to do is I'm going to make a copy of that page. So I copy whatever page was there. I make it a new entry. I update this entry, say it was this guy. I put a point here, and now I'm going to say read write. And now the parent has his own private copy of that physical memory, or that copy of the memory he can actually read and write to.
So isn't that problematic if you have the parent making its own copy of the reference one and the child makes a copy as well? Wouldn't it be better if the kernel somehow figured out, okay, this one's going to get the copy, this one's going to maintain the base one, so then you don't need, this way you're wasting a page.
Not really, because okay, here now the reference count for this thing is 1, right? So if the child ever wanted to write to this page, then it didn't have to make a copy because it knew it's the only one that has it. I think this is what the point of the video is.
Sure.
Yep, does that make sense? Of course, that's like a next level of optimization, right? Yeah, you can get them really into now obsessing about saving space and avoiding physical page allocations. Yeah.
So when that happens, is the parent creating a new page table, or just
maybe both. Maybe both. It depends, right? I mean, it might actually require a new page table entry too. Yeah.
I'm a little confused about how it's not copied. Can you just also make a copy? Whereas
I do. I made the copy lazily, right, on the bench. So it was never, the scenario that we're actually trying to optimize is the following. Parent creates a child that's identical to itself. Then the child does an exec. And at that point, whatever was in the child's address space has to be wiped out anyway, which is going to get a total new address space. And so we saved all making this complete copy of the address space by just copying the page directory.
before you were also copying the page.
You still have to copy the page top level page directory. In fact, you have to copy one physical page of memory, namely the page that contains the page directory, but nothing else.
Yeah, but the old way, what else do you copy?
Oh, you copy the page tables and the actual physical memory, in fact. Yeah, and even all the pages that correspond to the virtual address space of this user, actually, we copied that too. So it was terrible. We had both the overhead of copying the actual virtual pages, basically, that constitute the child's address space, as well as the pages that are necessary to for the page tables for the child. So there's always in these schemes there are multiple pages floating around. There are the page table pages, and then the memory pages or virtual pages of the address space. And we were copying both of them. And this scheme requires to copy none of them, except for the top level page directory.
So you can mark copy and write on both the page directory and page table?
Yes, you can do that. Okay, so this is another cool trick, and you're going to implement this. In fact, you're going to implement this version on steroids, because you're going to do this in user space as opposed to in the kernel, which makes it even more interesting. I'll say a little bit more about that in a second. Okay, so this is all cool. Okay? There's more tricks you can do, and so let's talk about a couple more tricks. And again, I'm going to sketch them out exactly instead of completely. In one place I want to start hunting, whereas another place you can optimize things quite a bit. It's an exec. So let's look at an exec a little bit. So what happens in exec? Well, in exec we're going to read. Right. So for example, when you do whatever exec, whatever echo. Right? What it's going to do is going to look for a file named echo in using FU6 in the current directory, and if that's the case, it's going to read that file, right, and stick it into the address space of the process that you're actually executing. So what it literally is going to do is going to look in the files on this, right? Here's the file, and this piece of code. What does it do? This piece of code. I'll give you sort of a guess. It says it on the top, right? Right, literally what it does, it goes through, reads every block from the disk corresponding to file F, and sticks it in memory. So we're going to have literally a complete copy, correct, of f sitting here in memory. Make sense? And that's what this code does. Now, that's all perfectly fine, but let's say, so we basically allocated on demand, or like we're eagerly allocated all the pages corresponding to file F. It might be the case that there are pages or blocks of file F that we never use, right? The same way with sbreak and all the other things that we've done so far. So it seems much smarter, correct, to actually allocate it lazily. So another way of writing exec is to say, okay, great, we're going to have, the page directory. And so let's say there's some page table that corresponds to blocks, that actually holds, this range of memory, correct? What we're going to just do is say, good, well, we're going to mark them not mapped at all, right? For example, we've not set the U-bit, or whatever we want to do it. And note that, what we want to do with these guys is actually load them from the file system. Right? So set some bits here saying, this is a page that needs to be loaded from the file system. So then whenever, the application or the process actually uses a page with this file, we're going to get a page call, right? And so we're going to run into the trap code. And in trap code, we can do exactly what we're doing there, correct? We're going to go and say, like, this is a page that belongs to the file echo. Let's read, that 4 kilobyte block of the file f, load it in memory, and restart, the instruction. Right? Does that make sense? So this is called on-demand paging. And the advantages of this, in all the other schemes, we only pull in the pages from the file that actually we're using, and not the page that we're not using.
Is that actually faster, or does it just let you use less memory?
Well, so the main reason that people were very excited about this in the 60s and 70s is that it allows you to start programs very fast. Right? Because instead of having to copy, the disk was extremely slow, like 60s and 70s, and so it took forever to read any blocks from the thing. And so this allowed, gave much better interactive performance because you allocate one block and then maybe you're off the ground and the user gets some feedback. It can be if the page is not used. So on-demand paging comes with all kinds of additional levels of sophistication. Let's say you do get a fault, right? And you're not required to read one disk block, right? You could say I can read 10 disk blocks and map them all to 10 at the same time. And this was going to be a win, correct? If you can read 10 blocks at the same rate you can read one block, which actually turns out to be true for most magnetic disks, not for a solid-state disk, but for magnetic disks. So it turns out, like, you typically combine in on-demand paging with prefetching, as that's called. You're going to prefetch a couple pages you think you're likely to be using. Does that make sense? So there's a separate prefetching policy that most operating systems have to decide whether actually to read in more pages or more file blocks than one. Yeah.
So just to clarify, instead of actually loading the file, it just says the file is here and maps, for example,
Yep.
marks them as when you actually access this, then load.
Yeah, exactly. That's exactly the point here. Does that make sense? And it's sort of actually not that dissimilar from what you did in your homework, correct? Basically the trap function will run and you will look at the page table entry and you will decide whether to dynamically allocate a page or zero it out or actually load it from the file system. It doesn't really matter. Yeah.
Where do you store which file it's going to come from?
Well, typically what you will do, okay, there's multiple ways of doing this. One thing, if you're very, very lazy, you can stick an INO number here and the offset of the INO number in the spare bits that are not being used. The other way of doing it, which is like probably the more standard way of doing it, is just keeping a separate table on the side, saying, oh, this page actually belongs to this particular file, or is located in that file. And then you have to have some bits saying here, this is a file-backed page. And then you look in your file-backed table with like information about pages. Yeah.
So as far as kernel specific programs, would you do something similar on-demand paging?
Yeah, people don't typically do it for the kernel because you could do it, correct? So let me actually, this is the next trick I wanted to talk about. Once you have this in place, there's obviously you can do more. Let's say the file actually is bigger than fits in physical memory. It could happen, right? I mean, the disk is typically larger than physical memory, so you could have a file that So let's say this file is, we were like, what's the maximum? Let's say this file is for, 16 gigabytes. No way that fits in x86 memory or in your JOS setup, correct? And so if we were playing this game, correct, we said so far, we want the main paging, no, well, let's say we have 2 gigabytes of free memory, to actually fit in the file. So we can read 2 gigabytes of the file, correct? And every time we get a page fault, we put the page in memory, we read it from the block from the disk, put the block in the memory, and keep on going until we fill up, right? So at some point, we're going to get a trap, and we're going to call this function whatever kalloc, and kalloc says, yeah, too bad, I don't have any memory anymore. So what then? Are we toast, or what could we do? Yeah, go ahead.
You throw away at the first page of the file and cycle around.
Yeah, you can. So this is called page replacement, correct? So this is the next trick is like on the main paging plus place replacement. If you decide you don't have any physical memory and you need physical memory, well, the only option you have is to throw out something. Right? And so the next trick is to say, okay, good. I'm out of memory, no problem. I got 2 gigabytes of memory. Surely there's something I'm not using, so I'm going to throw out something that I'm not using. Clearly, in that light, the prefetching, there's going to be policies that decide what to throw out. Right? And you've seen this. This is the same as in caching in 004 or any other place. There's a whole range of different policies you can imagine. One popular one, which I think you refer to, is like something called LRU, least reasonably used. You look for your 2 gigabytes of memory. You decide, which page was the one that I used least recently. So that means that is the page I used far away in the past. And that's the page I'm going to throw out. I'm going to throw that out with the assumption that that's probably not going to be, not likely it's going to be used anytime soon. Right? And of course, that assumption could be wrong, but then you have to do this again. But if the assumption is right, you have a little while free memory for a while to go. Make sense? Good. So now this is another. What kind of other cool thing does this give us? This gives us actually, we're now going to be able to run programs that are bigger than physical memory. Right? So now we can run user programs that actually don't fit in physical memory. And that's only basically the virtual memory stuff that we have. But this is like falls in this category like a new feature. Right? We get things that we couldn't run before, we can run now. Will every program, if the program is bigger than physical memory, will run fast? Well, it depends, correct? It depends on something that's called, the concept is called the working set. If you look at the working set of an application, which is basically all the pages that it uses frequently, if the working set of the application does fit in physical memory, then we're in good shape, correct? If we're like basically always fits, but once in a while we go out to disk to actually get some page. That's going to work out fine. If the application uses much more physical memory than it really is in the machine, we're going to be paging in and out continuously, correct? And the program will run extremely slow. Make sense? We're not going to implement, you don't have to implement on-demand paging, although in our user level file system it does something like it. In JOS, in Lab 5, you'll be looking at that a little bit. One thing to think about is, I remember, you might have seen this in the schedule, the last couple of weeks of the term, you can do anything you like. You can do a default project, which is Lab 6, or you can do your own project. And one of the things you can do is like take one of these, or many of these tricks, and only implement them in your operating system, and see if they work out. So that is on-demand paging plus page replacement. Now we're going to do, there's more crazy stuff you can do. There's no limit to virtual memory tricks. So one other thing actually I want to quickly point out is notice that actually the file is sitting in memory. Right? Now the typical way we've been interacting with files in Unix is through open, read, write system calls. Right? You open a file, you read a block, or you write a block, you close it. If you want to change where you're writing the file, you have to call this function lseek to move the offset pointer to a different place. Right? So lseek, for example, moves this pointer, or at least lseek moves the pointer here on disk in the file. But notice that the file is actually sitting in memory also. So another thing you can do, instead of using the Unix read and write system calls, you can just like use load and store instructions, right, to actually read and write. And if the policy is that if you do a write to the file and then at some point you call say close, or you say like, well then flush out the changes to the disk, that would be a perfectly fine way of doing it, correct? And what is the advantage of this? Well, the advantage of this is great that you can just like jump around in the file easily, because you can just reference to a particular offset directly using load and store convention. Make sense? So this is called memory map files. And every Unix operating system has it. And the system call that goes along with that is mmap.
So if you do the memory map files, can you do better on the close than like just writing the entire file back to disk?
So first of all, close doesn't write the file back to disk.
Flush.
Yeah, flush does, and you could do better because you can read, you could do interesting optimizations. But the same thing you could do with write. You can just delay all the writes to the flush and then write them back. Write doesn't guarantee, like the Unix semantics of write doesn't guarantee when you call write, it's not write through. It's write back. So at some point in the future, it might write the file system, the file back to disk. We're going to talk a lot about that when we talk about file systems. But yeah.
So if you write to a page, will its version get set?
Yes.
How you detect web?
Yeah. So there's two things maybe that's worth looking at. Let me scroll back to see if I still have page info lying around. You see the D bit? That means that page was written somewhere in the time of the page. And that A bit, any guess what that A bit is? That was accessed. And why do we care about access? Well, we want to implement LRU, right? So we need to find out like which pages have been accessed in the last period of time. Make sense? Yeah.
Does that even something to do with how like the cycles has been accessed, or?
No, I know. Just it has been accessed since the last time you changed your PTE. So if you want to know like which, if you want to figure out in the last 10 seconds, or last millisecond which page got accessed, you have to first clear all the A bits, then wait a millisecond, and you look at which pages have been accessed. All good? So I hope like virtual memory is getting more and more exciting. And you see here the power of this level of indirection, right? Like, this simple idea of sticking a page table certainly gives us an enormous freedom of doing all kinds of interesting things. So one more, and then I'll talk about Josh. So this is another crazy one. All the ones I talked about so far, actually almost all operating systems support them. This one almost no operating system supports, but nevertheless fun. At least things to think about. And here's the idea. Let's say you have two machines. Here's machine 1. Here's machine 2. And they're connected by a network. But you didn't have the money, and you couldn't buy a machine actually with physical shared memory. So like normally, maybe you have a machine that has physical memory. It's actually shared between both the two machines. But let's say you didn't have the money to buy it, like your student couldn't afford to buy expensive memory machines. So your machine just has no shared memory, but of course it has some local memory. Every machine has it. Now you can play a trick, right? What you can say is like, well, I'm going to run some application. I'm going to take some part of the address space, and I'm going to declare that part of the address space as shared. This is often called shared virtual memory. And now let's say M1 and M2 want to share that virtual memory. Well, what they do is like they both have a page table, right? And they mark, say, when they start, one of them gets it in write, and one gets it in no mode, like nothing, empty. And so for that machine, that page is not mapped here. This page is mapped. But let's say this guy actually wants to access that same memory. Well, what will happen? We'll get a page fault. Right? So the kernel will see page fault. Maybe the kernel says, this is part of my shared virtual memory space. I'm going to fetch that page. But instead of fetching it from disk, I'm going to send a message to machine 1 saying, like, hey, please, I want that page. So what does this guy do? Well, this guy, of course, can't write anymore to it because it's going to go over there. So you can clear out the write bit, set it to 0, right? ship over the page to machine 2. It sticks it in its physical memory, updates its page table, it's all right, and now it can run. Right? So now this guy can write like one hit. See? And that's what this guy says, I want to read this page again. Right? Well, same thing happens. This gets actually page fault, correct? This goes ships like, hey, I need your page back. So whatever, this guy, moves it from memory, sets this to 0, sends the page back to over here. It makes it, puts it in physical memory, updates the page tables, and sets the write bit. And boom. So now we have basically what's called virtual shared memory. Because the pages are flying back and forth, and we can read and write each other pages even though we don't have physical shared memory. Now, if you think about it, the way I described it is extremely inefficient. But maybe a trick that you can play is you can make copies. Like some pages may be mostly red. Well, you can map those both read, correct, to both address spaces, have a copy of both of them in each on its physical memory, and at least for the pages that are mapped read-only, correct, they can be accessed very, very fast. So if the writes are not happening that often, or at least write conflicts to the same page is not happening that often, that actually could perform reasonably well. Right? Does that make sense? Everybody understand how this goes? So this is it's called shared virtual memory. It's a cool trick. It's not being used quite a bit. We always have a bunch of students in either 804 or 808 who want to implement this. And it's sort of cool, right? Because you have a cheap way of doing virtual memory, or shared memory. Make sense? All right, so this is one. The last trick was like, a trick that very, very few people use. There wasn't an operating system in the 80s, Apollo, that actually had this as its foundation. And every memory basically across all the machines was shared. And sort of like, even if you had a distributed system, it behaved like a single physical machine. Company doesn't exist anymore, but I think that's unrelated to this trick of shared virtual memory. It was one of the early workstation companies. Okay, so I want to talk a little bit about JAWS very quickly. I'm sure we'll get more time to talk about it. So let's quickly, so JAWS, so the memory layout in JAWS is not unlike the one in x86, except it's more complicated. And the reason is that because a large part of the operating system that you're implementing is running in user space. Right? Remember, the JAWS kernel itself is very minimal, and almost all the interesting functionality is actually implemented in user space. That means that the user space has to have a lot of control over components, correct? And so one way to get a lot of control over components is actually having that show up in the address space so that the user application can manipulate it. And so there's a couple of things. And there is a kernel base. It actually sits higher than in x86, so the amount of physical memory that actually is even smaller. And the kernel sits very high in that top. The reason that the kernel is so small is we can put it high up. Right? There's a bunch of stacks that sit below that, and there's one per processor. Not so interesting. Then there's some memory mapped I/O, not so interesting. And then there's a couple of other things that are interesting. All the proc structures, which are called environment structures in JAWS, are mapped read-only to user space. So user programs can directly look in the proc structure. And that's going to be useful for a number of things you're going to be implementing, like sending IPC from one process to another, from one environment to another environment. Similarly, all the page info structures that you're actually set up, correct, for Lab 2. Who's done with Lab 2 actually? How many people are done with Lab 2? Oh, good. You guys are going to be busy. I hope you're at least at the end part. Hopefully everybody has done this part of the Lab 2. Right? You allocated page info structures to set up the physical memory allocation and all that stuff. Those structures are all going to be mapped. In fact, you do that in the last part of the lab. They're going to be mapped read-only to user space so that the user program can see which page is actually being allocated. What can I use? There's a user exception stack. One of the things you're going to be doing in, I think it's lab 4, is you're going to remember we have been looking at these trap calls, correct, all the time. And the kernel gets a trap call, and then the kernel does something, and then it resumes. Now, since a lot of the operating system functionality is implemented in user space, those trap calls have to go to user space, right? Because that's where the operating system that actually needs to do. So we need a way of sort of rerouting kernel level traps back up to user space. And so we're going to use that exception stack to do that. And so your traps are being propagated from the kernel back into user space, where then you can do all kinds of interesting things, including like looking at your page tables and playing the same tricks that we've been talking about. In fact, this allows you to implement user-level copy on write fork. That's probably one of the more tricky pieces of code that you actually will have to implement. And so to give you a feel, like, again, it sort of shows like how powerful if you can expose the structure to user space, then the user application can also do all these cool tricks. Right? And one of the advantages of that particular kernel architecture. And then, like any other, we noticed that we allocate some guard pages. Here's a guard page that sits right below the user exception stack, just to make sure that if you run off your exception stack, you get an error as opposed to scribbling over some memory that you might be using. We added this in later years. The first time in the first couple of years at 828, we didn't have this. This made the debugging life of the TAs a lot more complicated, and your lives. And now it's simpler because you get an error. And so then there's basically, the user part of the process sits in the bottom part. Yeah.
What's the motivation behind doing user space copy running? Is it faster or is it simpler to do?
Flexibility. The application can actually decide to do it. Right? Like if you decide you don't need it, you don't have to. If you decide you want it, you can use it. But this comes back. Let's revisit this topic. It's a good deep question in some sense, right? What is the advantage of a sort of a JOS kernel style versus XV6? And in a little while, when you have implemented more of JOS, we'll return to that discussion, and then presumably it's easier to have the discussion because you understand better what JOS can do. Okay. So then okay, so I'm not going to be able to do justice to this, so I'm going to do this again on Monday. There's a very cool trick that JOS uses to make page tables look like a single array of page table entries. Like in PageDir walk, right, you have to walk through the first page directory, then the page table entry. It's sort of annoying, right? It would be nice if you know the physical page number, but the virtual page number, if you could just index in an array and get the PTE, right? And VPT allows you to do this. And the way it works, I'm gonna talk about it on Monday because it's just too short. I can't do it in 2 minutes. Or I can do it in 2 minutes, but I'm not sure you would appreciate it. What it does, it recursively remaps the page directory into the address space. And so just to I think the address for this is 3BD. And that actually, at 3BD, what you're going to be doing, you're going to map the page directory at 3BD. So what does that mean? Well, what you're going to be doing, you're going to make it loop around. You're going to take the first top level 10 bits, index that in that, and where is that going to get you? It's going to get you back into the page directory. And you're like, why is that any good? Well, remember the next 10 bits are going to tell you which page table entry, which page table to use. And so the next 10 bits are going to give you the page table. And then the next bits are going to give you the page table entry. And boom, using a single address, if you go through through this particular page, you actually get the PT entry. And if you don't get this, don't worry about it, because I'll talk about it Monday. I'll go through an example just to illustrate what it is. But you should draw this out. There's a bunch of documentation. This will show up in lab 4, and where you actually have to set this up. And the right thing to do is like take a couple of addresses and work them through and see indeed if it works out correctly. But this is basically a very clever trick to avoid having to write PageDir walk, so that you could just do PPT, array open, n, where n is some virtual page number, and boom, you have the PTE in your hand. All right? So I'll talk about it on Monday a little bit more, but that will conclude the virtual memory. All right? Good luck with lab 2.